In the last video, we saw that if you took some solid zinc and stuck it in a solution of copper sulfate, that the zinc will essentially give electrons to the copper. So then you have zinc cations that are in the solution. So essentially, it will become a solution of zinc sulfate. And the copper, once it gets those 2 electrons, is going to go into its neutral, its solid state, and it's going to precipitate out of the solution. And we saw the reaction right over here, solid zinc plus copper sulfate in solution in water. It's an aqueous solution. You have the copper, the solid copper precipitating out, and now it's a solution of zinc sulfate. That the zinc has essentially been oxidized. It lost 2 electrons. It went from neutral to positive, and the copper went from positive to neutral. So the copper took those 2 electrons. Zinc was oxidized by copper. It lost electrons to the copper. Copper was reduced by zinc. Its charge was reduced by zinc. It gained electrons from zinc. Now, this by itself is interesting. It's an interesting redox reaction. Something was oxidized, something was reduced. But wouldn't it be interesting is if we could somehow somewhat separate these 2 half reactions and make these electrons travel over a wire. Now, why would that be interesting to make electrons travel over a wire? Well, if electrons traveling over a wire, that's a current. And you can make current do useful things like power a motor or a light or whatever it might be. And so essentially, if we can do that, we would have constructed something of a battery. And if we can keep that going, if we can keep the current flowing, we would have constructed something like a battery. And what I have here, this is a picture of a galvanic, sometimes called a voltaic cell. And this is doing exactly that. It's separating these 2 half reactions. And it's separating them with a wire. So zinc can give copper its electrons, but it forces the electrons to go along this wire and produce an actual current. So let's think about why this is working. So you have solid zinc right over here. We've already said that, look, the solid zinc wouldn't mind giving its electrons to copper. Copper wouldn't mind taking it. Copper is more electronegative. And so you have a reality where the solid zinc could give away its 2 electrons and become the cation zinc, so a positive charge, and then it dissolves in the water. Once it has that positive charge, it's easy to dissolve into a polar solvent like water. And then you have those 2 electrons. Where are those 2 electrons going to go? Those 2 electrons can then go and be given to the copper. And both zinc and copper are great conductors of electricity. They're transition metals. They have these seas of electrons. So electrons can travel within them fairly easily. And so you have your 2 electrons. So those are your 2 electrons that I showed traveling in green. And they can come all the way to the bottom of where this copper bar is in contact with the copper sulfate solution. And now you're going to have an atom, a cation, I should say, an ion of copper, that when it comes in contact with those electrons, it's going to nab them up. It's going to nab them up and become neutral. So it's going to nab them up and become neutral. And when it becomes neutral, it's going to precipitate out of the solution. It's going to precipitate onto that bar. Now, you might be saying, look, if more and more positive things, if more and more of this zinc, this positive zinc is flowing in this, wouldn't this make this an imbalance? And if this solution becomes too positive, then the electrons wouldn't want to leave as much anymore. So if you just have a bunch of, if this starts becoming very, 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 very positive. And similarly, if all of the positive stuff, if all of the copper cations are capturing the electrons, this solution is going to become more and more negative. It's going to have more sulfate and less of the positively charged copper ions. So what can we do to make sure that that doesn't happen too quickly? Well, what we do is we use something called a salt bridge. And this salt bridge right over here, salt bridge, this helps neutralize that effect that we just talked about. And with a salt bridge, you can kind of view it. It's not going to be liquid, because then everything inside of it would just fall out. You can kind of view it as a goo of a salt. In this diagram, we picked sodium sulfate as our salt. So for every sulfate molecule, you have sulfate anion, you have 2 sodium two sodium cations. And so what's going to naturally happen here? Well, as this becomes more and more positively charged, as more and more positive zinc ions go into the solution, the negative sulfate ions are going to want to come out of here. So the negative sulfate ions are going to want to leave all of their negative friends right over here, go into the salt bridge, and then the ones that are already in the salt bridge are going to want to come out here. Similarly, the sodium right over here will be tempted to help neutralize. The sodium could go in this direction. Let me do it this way. Could go in this direction and help neutralize any net negativity that's happening there. And so that will keep each of these solutions from becoming too positive or too negative and allow this current to continue to flow and do useful things.